Welcome to the short discussion on axial deformations in bars of varying section. This is also part of the Unit 1 stresses and strains in the course strength of materials 1. So, in this particular topic, we are going to see uh, how to calculate the axial deformations in the bars, which may be varied in their cross section. For example, it may be change in the cross section size, whether it increase or decrease, or it may be of different cross sections, such as combination of rectangular, circular, and so on. Okay. Uh, by the end of this session, I would like to know, communicate, and expect the learners to get these points. What is the concept of bars of varying sections, and how to calculate the total elongation in those bars having varying sections, and look at some practical examples of such varying sections. Here you can see that there is a shaft where the diameter has been continuously changing. There is some cross section area available here, reduced cross section area. Sometimes it may be of 2-3 steps, right? Or you can see a bicycle here where you can find different cross sections. All are circular shape, but of different cross sections. Some of them are having more area, some of them are having less area. Uh, so in this case, so when it is subject to some kind of force, how to calculate the axial deformation? What is the total elongation that can be resulted from such kind of loading, axial loading? So that is our task. Let's see how to calculate that. So if you take a single bar, we know this analysis. If you take a single bar and or cylinder, you can say, and if you apply some force, a pulling force, or you can even apply a push force for the same. If you apply a pulling force, it will be extended. You can see this is the modified shape of the cylinder or a bar, right? So initially it is L, and now it has been stretched out by an additional amount delta L. So the strain resulting from such kind of loading is delta L by L is for the strain. So we know these basic formulas, that is stress is nothing but load by cross sectional area, and from the Hooke's law we have a relationship like linear relationship between sigma and epsilon, that is stress and strain. Because they are proportional to the elastic limit, we will replace that in proportionality by a constant x modulus. Sigma is nothing but E epsilon. Now we are already the formulation for strain. Let us substitute that here. So you are going to get E times epsilon, sorry, delta L by L. In place of epsilon, you can write delta L by L. That is equal to your load by area, because stress is nothing but load by area. If you rearrange the terms, because our task is to get delta L, so keep delta L on one side, rest of the things send them to the other side. So then what happens? Delta L is equal to PL by P. So this is the basic formulation for calculating axial deformations, right? So most of the times, when we are dealing with problems, this is very much useful, this formulation, because in practical problems mostly you will be aware of the deformations can be measured with some kind of deflectometers, right? Um, uh, what you call dial gauges, and from there you may be required to calculate the stresses that are experienced by those bodies, right? So mostly we will be knowing these values. So from there you may be asked to calculate the stresses, right? So this is very important formula, very basic formula, but for all calculation of the forces acting on the members or stresses in the members, right? You can use this formula to find. Here A is called axial rigidity. So there are mostly we deal in Chandra is three kind of rigidity. One is axial rigidity, next is flexural rigidity EI. Later on we will see in the chapter of pure bending, right, pure flexure. There we come across another rigidity called flexural rigidity represented by EI. And when you are dealing with the torsional chapter, torsion, you are getting torsional rigidity called GJ, where G is the shear modulus and J is the polar modulus of modulus, right? So let's see with the help of this particular formulation. Now, if we consider a varying cross section, maybe it is comprised of 2-3 parts. How to calculate the total deformation? So let us consider a staple bar like this. Here we are having a staple bar, varying cross section here, with the three different steps are there, three different cross section you can see here, and it is totally subject by a common force. It is pulled by a common force P on either side. In such case, I am required to calculate each, either like I may be asked to calculate stresses, or I may be calculate the total deformation that can be resulting from the kind of loading that is applied here. So here, if we look at the terminology, the details of each of the particular bars, B is the force acting, and A1, A2, A3 are the cross-sectional areas of this section 1, 2, 3 respectively, and the corresponding lengths of L1, L2, and L3. Right? Now, here it may not be all or maybe not be a circular or rectangular. It may be a combination sometimes. So accordingly, we may have to take the radians. For example, it is circular. We may take pi r square or pi d square by 4 in the diameter, or if it is rectangular, we can accordingly calculate. And here E is the Young's modulus of velocity, which we know. Now, if you want to calculate stress, this is a direct one. Each bar you can calculate the stress because the load is same for all. So load by that particular cross sectional area. If we divide that load with that particular cross section, it may be a rectangular or circular or square, whatever it may be, the shape of the bar. Accordingly, you can use that area and get the value of stress in that particular portion. Similarly, in section 2 and 3 also you can get using this basic formulas V2 and V3, nothing but load by the corresponding area of the bar. Right? And then here to get the strains in different sections are obtained. Right? Once you calculate this stresses, then you can get the strain, because there is a linear relationship between stress and strain as per the Hooke's law. Then we will be able to get this epsilon 1 is nothing but U1 by E, where P1 can be replaced by P by A1. Similarly, you can get epsilon 2 and epsilon 3, the strain in the section 2, strain in the section 3. Now, according to the definition of that strain, you can replace with dl1 by d1. L1 and dl2 by L2 and so on. Then you will be getting the deformation, the elongation in each part. Elongation in each part you can calculate as dl1, dl2 and dl3. So dl1, if you want, that becomes dl1 by a1e, provided the Young's modulus is. Sometimes Young's modulus may also change. Right? Mostly, these kind of varying bars generally don't vary the Young's modulus, but it can be varied when it is made out of dissimilar materials. You may be taking the Young's modulus different. So like that, you will be taking all the P L1 by A1 A1, because force P is common for all. So what are the varying point is L1 A1, and if it is Young's modulus, if all are made of same material, Young's modulus may not change. Otherwise, it may also change. So calculating all this, you will be getting these deformations in individual parts. But I am interested in the total deformation. I can simply club them up. DL1, DL2, DL3, and I will get the total deformation in the entire bar as PL1, P by E times L1 by A1 plus L2 by A2 and So finally, what I am going to get if I put the common terms out, P by E times L1 by A1 plus L2 by A2. Remember here Young's modulus is same for all the materials. In case if this is made up of different materials, this Young's modulus will be also inside because each for each case it will be different. So here it becomes A1 E1, A2 E2 and A3. So that is the concept as far as the theoretical background is concerned. This is how we can calculate the total elongation in the bars of varying cross section subject to the axial load. Right? Now let us look at a numerical example to have a better understanding on this topic. Uh, you can see here there is a stepped, three-stepped bar having three sections here, and there is a pull of 35 kilonewton is acting on this bar, and three lengths are available, and the Young's modulus, of course, it is made of same material, so length steel 2.1 times 10 to the power of 5, and he is asking us to calculate what is the stresses in each section and what is the total extension of the bar. So if that is the situation, we can simply use that formula, right? DL1 as B1 L1 by A1E and E2 L2 by A2E and so on. And similarly, if you want simply stresses, stress is nothing but load by area. You can calculate the load is there common for all the bars. The area is changing, but we can calculate and finally get the solution what you want. So here, in such kind of problems, you can straight away solve with these two steps. So first of all, recognize what was given, right? What are the unknowns that we are supposed to find? What are the knowns that are given? And look at the relationship between them. Then you can get easily the solution for this. So if you systematically mark it, what are the unknown quantities in this problem is stresses in each section. So he is asking us what is sigma 1 and this stress in this, stress in this, and then sigma 1, 2 and 3. And if you want to calculate the total extent, he is also asking total extent. Total extension is delta. And we are having, these are the quantities that we are already being given. So P is the common force, so all along it will stay same force will be acting. So P1, P2, P3 becomes same 35 kilonewton or 35,000 newtons. L1 is 20, L2 is 25, and this is 20. It is important to make all of them to be consistent in general for all these problems, because we stress is generally expressed in Newton per mm square. We can convert any force units that are available in newtons, and if there is any kind of length units or the distance measurements, we generally representing in mm. Similarly, the area units. So if you convert them, keep it ready so that we can simply use the formula. So in this case, if you are interested to calculate sigma 1, we know straight away sigma 1 is nothing but E1 by A1 and so on. P is common for all, so you don't have to write P1. P is the same. And A1 is simply available here, so you can use this by tenfold. Then you will be similarly you will be getting sigma 2 as well as sigma 3, namely P by A2 and P by A3 respectively. Okay. Now, if you are interested in this, just now we have written the formula first. The total deformation, of course, one bar it is P L1 by A1 E1. Of course, E is same, so L1 A1 E for first section. This is the deformation resulting from the loop. Same, we can calculate for section 2 E2 L by A2 E2. That's it for the solution there. Of course, E is same as we just now told. All are can replace with the I can take common even 2.1 times 10 to the power 5 come to the front side, and within the brackets there will be even p is also same. So p by e can be taken common, and we can simply calculate L1 by A1 plus L2 by A2 summation multiply with p by e, and we get the solution like this. Okay. So this is p by e times L1 by A1 L2 by A2 and L3 by A3. So we will be getting, this is the final solution. That's all about this topic on axial deformations in the bar saw.